All right, so physics. We'll start off by looking at a definition. Now, this PowerPoint is extremely detailed. I'll just be like highlighting certain things, so don't think, oh, I've got to copy down every single thing on the screen. Okay, one, that's not taking notes. Two, we won't have time for that. Okay, so as you're preparing to go to college, you're not going to be able to hold on to every single word the professor says or every single thing they put on the screen. So that's what learning how to take notes means. You get the most important parts, and then we move on from there. Okay. So with that in mind, definition of physics. Pretty much, that's pretty important for us to know. Okay. It's a study of the fundamental laws of nature. Okay. So that is a pretty broad definition. So that means anything from atoms, subatomic particles, all the way up to a galaxy. Okay, that comes into the purview of physics. So our goal in physics is to get a deeper understanding of our world, the world that we live in. Again, from the tiniest little subatomic particle to the entire universe. Okay. All right, so what we get from here on out is going to sort of be review, okay? Let's see if I can go back to that. Again, I'm going to underline things and highlight things. That's the key things you'll need to make sure that you get. All the other stuff is sort of fluff. And this comes from your textbook, so it should model your textbook. Come on, are you not going to let me? Ah, there we go. That's what I want. There we go. Oh, fiddlesticks. We ran into this last year. All right, so physics is one of the many natural sciences. Pretty much any science you've studied, chemistry, biology, geology, all those are considered natural sciences. And science in general is just an organized way of thinking about the world that we live in. It's a process. It's not just collecting a bunch of facts and that's it. It's a process. So that means we have the scientific method. Okay. Scientists' goal is to try to explain or find explanations for observations that they see, for knowledge that they gained about certain events. All right, so scientific method, make sure you write down these 4 steps because pretty much that's what we summarize the scientific method into, these 4 steps. Observation, inference and hypothesis, test and conclusions. Now my stool is too tall. There we go. So scientific method always starts with a question or an observation, like, well, I wonder why that happens. Okay. Then we start to make some inferences or form some hypotheses. I think this happens because. Okay. And then we come up with an experiment to test that hypothesis. And based on the results of that experiment, we come to a conclusion. Okay. I have those 4. Okay. Let's see. A couple of things to mention out of here. Of course, we start with an observation. Well, I already said that. Observations lead to inferences. So if you want to kind of write this out, here we go. Observations, that's where we always start. That leads to an inference or a hypothesis. Kind of need to know what the definitions of those words are. A lot of times on a test or quiz, they'll say infer. You need to know what that means. So an inference is a logical interpretation. A hypothesis is a detailed scientific explanation for a set of observations that can be verified by experiments or rejected by experiments. So you need to know what we're talking about when we mention those two words. When we infer something, that's where we just have a logical interpretation of something um, based on some observations that we've seen. Okay, so I can look at something and infer that. So if I can infer that all of y'all are very self-motivated people because you're sitting here in this class today. That's an observation. I'm observing you sitting here. I'm observing that you're all working. So I'm going to infer that y'all are hardworking, self-motivating people. Does that necessarily make it absolutely true that you are? Not really, because you could be, I'm only in here because mom and daddy make me come in here. Okay. And that's probably true. That was true in my case as a teenager. It's like, I don't know, parents make me come, so I have to come. But while I was in there, I was working hard. Okay. Um, Hypothesis is a detailed scientific explanation for a set of observations, but the difference is that you can verify or reject it by experimentation. So you have to be able to do an experiment to try and prove your hypothesis correct or to have it proven incorrect, okay, or rejected. All right, so let's go on. I wouldn't write any of this down just yet. So experiment that disagrees with your hypothesis, that we say that is rejects the hypothesis. So we have to come along, we have to make some tweaks to our hypothesis. Yeah, we'll skip through that. Those are just examples. Another definition that we need to make sure we know is theory. Scientific theory is a detailed explanation of some aspects of nature that account for a set of well-tested hypotheses. So after we have our hypotheses and we have done experiments on it and our experiments have verified that hypothesis over and over and over again, then we can say that that is a scientific theory. Okay? So theories are well supported explanations. So we have to have lots and lots of experimentation that backs up our hypothesis before it becomes a scientific theory. So the key word there is well supported. An example. Now, this was a little confusing to me at first, so I actually had to do a little research about it. Because the example they give in the book is about gravity. Well, I always thought of gravity more as a law. Like, it's not going to change, okay? But there are two aspects of gravity that they're looking at. One aspect of gravity holds as a scientific theory, whereas the other aspect of gravity holds as a law. And we'll get into that in just a second. So an example, and I would write this down so that, because like I said, it was confusing to me too. An example is the theory of gravity, which explains why an object falls with constant acceleration to the surface of the earth. Okay, so usually when we think of the law of gravity, we think of gravity being, well, if I drop something, it's going to fall because of gravity. That's the law of gravitation, that it will be attracted to the earth and it will fall to the earth. The theory that they're talking about here is why? Why does it fall to the earth? Why doesn't it just float away, or just stay right where it's at? Okay. So an explanation of why that happens or doesn't happen is considered a theory. Okay. We have lots of experimentation that's been done on that and that supports our hypotheses for it. But we can't cross over and call it a law. Okay. That aspect of it anyway. Now, so that's a scientific theory. Law, on the other hand, laws of nature are well-supported descriptions of nature. So we have something like the law of the conservation of energy. We call that a law, or the 3 laws of thermodynamics. We call those laws because they describe what's happening. They don't tell us why. Law of conservation of energy says energy cannot be created or destroyed, period. Boom. Doesn't tell us why. Okay? The law of gravitation tells us that if I drop this, it will fall to the earth, period. Doesn't really tell me why. Okay? So there's your difference in those 2 definitions, and sometimes that can get a little hairy. So theories try to explain why or how something happens. Laws describe something that's happening. Okay, so there's your biggest differences between those 2 things. Okay. So if you do an experiment and your experiment agrees with your hypothesis, then we can say that you are validating that scientific theory. Okay. But if your experiment does not agree, then we have to reject or discard that as a theory and tweak it, change it, and retest it again. Does that make sense? Okay, now, where's my little... I ought to be able to move this around, right? I can. Yay. Maybe that'll work. All right. So laws do not provide explanations. We already talked about that. If a new observation agrees with the theory, then we can say disagrees, then the theory has to be disregarded and we have to start over. We already talked about that. Okay, so technology. Technology is basically taking what we learn in science and making it applicable to make our lives easier. Okay? So right now, all of you are holding some form of technology in your hand. What is it? Your pencil, your pen. Those are forms of technology because they make your life a whole lot easier, right? It would be a whole lot harder to write without one of those. We'd be, carving things out. That wouldn't be a whole lot of fun. But we have looked at properties of things like graphite and developing solutions of ink and things like that. And we've taken that knowledge that we have and then we applied it and we made pens and pencils and writing utensils to make our life easier. Computer obviously is one, but I want you to know that it doesn't always have to be something digital or computerized to be technology. The fork that you ate with this morning or the spoon or whatever, that's a form of technology because it sure made your life easier, right? Okay, so that's what we do with technology. We take knowledge that we have learned or gained in science and we apply it to make our lives better. Maybe not necessarily easy, it could be better. And that's a technological development. Okay. Now, knowing how to do something and knowing how something works isn't the same as knowing how it's best to be used. Okay, let me restate that. Just because we know how to do something doesn't necessarily mean we should do it, right? Okay. That's where scientists and politicians and the general public have to stay informed. And this is why you're in school taking science all the way through high school, so that you can become an informed public. Because one day, and one day soon, you will be voting on things. So scientists do things, we come up with this new knowledge, and it's politicians and other people who decide, should that really be done? Do we really need to be able to do that or not? Well, it's what you're the ones who wind up voting for those politicians, who wind up voting for that technology to be used or not used. Okay? So you need to stay informed. You need to be able to read things and understand what they mean instead of just relying on everybody else to tell you, well, this is what this means. Okay? So that's why it's good for you to stay educated yourself. And sometimes misguidedly we say, well, I'm never going to use this in my life. Yeah, kind of are. You're living here and you're going to be a part of society and a part of the public, and you got to know stuff. Okay, so and there are lots of examples of that, and I'm just thinking of biologically, the whole debate of stem cell research and what type. That's just the one that pops in my head because I taught biology for so long. And what type of stem cell research are we able to do? Okay, we know scientifically that fetal stem cells are the most useful, I guess you'd say, because they can turn into anything at any time. So fetal stem cells can turn into liver cells and heart cells, and they can do all of it. Okay, adult stem cells, the ones you have in your body right now, they can regenerate some things, but they're limited. So at this point, we have banned human research with using fetal stem cells. Okay, hopefully our reasoning is obvious for why we banned that. Okay, but if you're somebody that doesn't look at the whole picture and you just say, hey, this could help cure everything, you think, oh wow, that sounds great, let's do. And then you've agreed to a problem and you're like, wait a minute, I didn't realize it meant all of that was going to happen. So you need to be able to be informed, and that's why we have some of the laws and the politicians and the groups that we have to try and say, hold on, just because we can do it doesn't mean we should do it. Okay, we can clone things, doesn't mean we should clone things. Okay, we probably have the technology and the ability to clone. We can do sheep. We've done sheep. We've done. I think there's maybe been a horse. There have been lots more than just the good old sheep that was cloned a long time ago. We've done more than that, but does that mean we need to continue and take that process to cloning a human being? Sounds like a sci-fi movie, but what kind of problems are we going to open up with that? So anyway, it's interesting. So you need to know these things so you can be informed people one day and not end up like a sci-fi horror movie. Okay, because it's possible. Anyway, so making decisions that affect society, people need to avoid bias. Remember what bias is. Bias is just your preference. And sometimes as humans, it's very hard for us to avoid bias. Extremely hard. As scientists, we need to try and do that as much as possible, in that, you're just like, okay, I'm just going to present my observations and my work. I'm not going to say whether it should or shouldn't be done. That is a question for society, political leaders, and voters and people in the public to decide. Moving on. That's kind of more of the same. More of the same. A lot of our new technologies that we have came from scientific advances that happened a long, long, long time ago. Einstein's theory of relativity, that was made a long time ago, way back in the 50s, is now the basis for a GPS system that you use on your phone all the time. Okay. Nuclear chemistry, in AP, we talked a little bit about this last year, but nuclear chemistry was the foundation of that started back in the 30s. The work with that started back in the 30s. And then at the end of the 40s, we had the development of the atomic bomb. But now we have even more useful technology, I guess you'd say, or positive technology, in that we use it to power cities. Okay, if you use it to power a large part of the Navy with nuclear ships, nuclear subs, and things like that. So we've taken that knowledge, and years down the road, we've used it for different technologies. All right. Now, this is another important thing that you need to write down. So, an important part of science is the ability for scientists in different locations to reproduce an experiment, to verify it, and get consistent results. Okay, so if I do an experiment here, and I have to be able to have someone do the same experiment in Germany and get the same results. Okay, so in order to take that process from a hypothesis to a scientific theory, we have to be able to have verifiable results. And it has to be verifiable no matter where you are. And it needs to be that any scientist anywhere can do my experiment and get my same results. Okay? So there's a lot of collaboration that has to go on. That is the reason that we have developed the metric system, or that the metric system was developed. Is so in scientific field, we all use the metric system so that we're all using the same form of measurement and therefore getting verifiable results. That's why we have significant figures. We didn't talk a whole lot about significant figures last year, but we'll go over them again this year. But that's why we use significant figures, so that results I get can be verified and be the same results as somebody who's doing the same experiment in Germany. And we can look at our results and say, oh yeah, we're getting the same thing. Okay, so results and experiment have to be verified. One of the ways we do that is developing the metric system. Got that? Oh, I forgot to erase it. Hang on. All right, lab safety, we've already talked about that, so we're not going to go into that anymore. Come on in. Yeah. All right, so again, there's a lot of stuff in here. We're just going to skim right through because we don't necessarily need it. So to get those verifiable results, the metric system is used. And in particular, we have what's called the MKS system, meters, kilograms, and seconds. So this is what you'll need to write down. Measurements always involve units. So our base unit for length is always going to be the meter, and we abbreviate that with an M. Okay. The base unit of time is always going to be seconds, and mass is always going to be kilograms. So that's where we get MKS. So in physics, we use the MKS system. Okay, so all of our lengths are always measured in meters, all of our masses are always measured in kilograms, and all of our seconds are always measured, time is measured in seconds. Okay. So, for example, well, no, I don't mean. Now, the next thing we're going to talk about is if everybody's got to do the same thing and going to use the same unit, we have to make sure that those units actually mean something concrete. Feet, where did the unit of feet come from? Does anybody know? Anybody know? Feet was a unit of measure for length, but it was based on the king's foot. So a foot was the size of the king's foot. Is that concrete? Like going to stay the same all the time no matter what? No, because you could have a really tall king who's got really big feet, or you could have a really short king who has really tiny feet. So the length can change, which is not very helpful when we're doing scientific experiments. We need something that's this length no matter what forever. So most of the time we think of a meter, we think, oh, well, it's a meter stick. Well, who made a meter stick that length? What makes a meter stick that length? So we're going to look at the standards that we use to make a meter, that what says a meter is actually a meter. If that makes sense. So, long time ago, we started coming up with these standards. And they've changed over time. Don't need that. Here we go. So, for a meter, the standard of length for a meter is the distance traveled by light in a vacuum. In 1,299,792,456 part of a second. Whew, that's a lot to say. Now, you don't have to memorize that. It's not, I'm just telling you where it is. It's not like I'm going to test you, and if you get one digit wrong, then I don't know, you're wrong. No. Just want you to know that that's where that meter stick comes from, that length. It's the distance that light travels in that teeny tiny fraction of a second. That's not going to change. Okay, that's going to stay, it's constant. And that's what we need. We need our units to be backed up by something that is constant. Okay. So that comes out to approximately 3.28 feet. And speaking of lengths of things, our towers, Peyton and Marco, y'all were second place. Kevin and Adam, first place. Braden and Landon and Luke, if your little tassely thing had stood up straight, you would have won. But it flopped over, and I couldn't get it to stand up straight. So, yeah. Okay. All right. So there's some typical distances. Again, you don't have to write that down. That's in your book. All right. So masses. Mass is a little bit different. Mass is still the only thing whose standard is an actual physical object. Because physical objects can change, like the king's foot, we tend to not like to use those as our standards, but mass is the only one that is still a physical object. So it is a platinum iridium cylinder, and it is protected in the Bureau of Weights and Measures in France. And it is kept in a very protected environment so that it doesn't change. Okay, so it's got two cylinders so that not even a speck of dust gets on it and changes the mass of it. So until we can find something that we can measure mass with that's not a physical object. So just know that 1 kilogram is an actual little cylinder. Right. Okay. The next one is time. And again, this table is in your book, so we're not going to go over that. Yeah, we do need to talk about this before we talk about time. So, the difference between weight and mass. Now, we throw those two words around as if they were the same thing, but they are not the same thing. Hopefully, remember that from physical science and stuff. Mass is an intrinsic quality. meaning it is unchanging. Intrinsic properties are properties that do not change regardless. Weight, on the other hand, is a measure of gravitational force. So it changes depending on your location. Okay? Mass is the same always, no matter where you are, whether you're here on Earth, whether you're on the top of Mount Everest, or whether you're on the moon. Your mass will be the same. Okay? But your weight will change depending on those locations. So you can take your weight here and it'll be one thing. You can go on the top of Mount Everest and it's going to be different. You can go to the moon and it'll be different still. You can go to Saturn and it'll be different there too. Okay? So because it just depends on the force of gravity, and the force of gravity can change depending on your location. Okay? If you're on the moon, your force of gravity is 1/6 what it is here on Earth. If you're on a planet like Saturn, it's going to be greater than what it is here on Earth. Okay, so it's just a matter of where you are. So please make sure that we understand that those two things can be very, very different. And when I say, so please do not say weight when you mean mass, because if you do, I will have to count that wrong. Okay? So don't use those interchangeably. All right, talking about time. Time is based on an atomic clock. Okay? So specifically, here's the standard measurement of time. It is, so 1 second is defined as the time it takes for the radiation from a cesium-133 to oscillate 9 billion and something times. So a cesium atom, the time it takes for it to vibrate 9 billion times, that's a second. That's pretty much what that means, okay? Oh, yeah. Speaking of time. We got that. That's a big number, so I'll leave that there for a second. 9,192,631,770 times. There we go. Okay. All right. And supposedly that is better than our old means of measuring time, because in old means, depending on the rotation of the Earth is not always exactly the same. It may slow down at some points, it speeds up at some points. So a clock can be off, okay? But cesium atom is going to vibrate all the time. And it's going to vibrate, for the most part, it's going to vibrate at the same speed all the time. So the time that it takes for that many vibrations is 1 second. All right. Prefixes. So we kind of know that already. So I'm just going to go to this screen and we're going to tell you the ones that you have to have memorized. Okay. And then that's going to lead us into good old dimensional analysis. Y'all remember that? Yay! Changing from one unit to another. You're going to be doing so many dimensional analysis conversions in this class. Okay. So you need to have memorized from mega all the way down to micro. Okay? So you need to know that mega is 1,000,000. So it's 1,000,000 times bigger. Kilo is 1,000, which you should remember that one from elementary. Hecto is 100. Deca is 10. So that's why we like the metric system. It's all prefixes of 10. It's all measures of 10. So 10 to the 6th, okay, that's 1,000,000. 10 to the 3rd, 3 zeros, that's kilo. 10 to the second, that's hecto. We got 2 zeros. You see the relationship between the exponent and the zeros. Okay. We got 6 zeros, we got exponent of 6. We got 3 zeros, 10 to the third. We got 100, we got 2 zeros, that's 10 to the second. 1 0, 10 would be 10 to the first power, that's deca. And then once we get past deca, we start going in the other direction. So deca, hecta, kilo, mega, those are all bigger than the base unit of meters or grams or seconds. Okay. But when we get to deci, we start going, they're smaller. So deci is 1/10. So we say that's 10 to the -1. It's smaller than a meter. Okay. Centi is 1/100th. And milli is 1/1000th. And micro is 1/1,000,000th. Okay, so 10 to the -6. The negative means it's a fraction, or it's in the numerator, or I'm sorry, denominator. And then the 6 means there's 6 zeros. Okay. All right. All the equations that we're going to use, and this will be on the next slide, and I'll underline it in just a second. But all equations in physics have to be dimensionally consistent. That means that it has to be length, or you have to make everything work out and cancel out to get the same unit on both sides of the equation. Okay, so that's why you're going to have to make sure you use your dimensional analysis so that you get those units to cancel out. Okay, so everybody got this down?
What is the macro symbol?
It is okay. That's a good question. The micro symbol is a Greek letter M, so it's kind of like you do a swoop and then you make an M. Yeah, it's a Greek letter. Sorry, it's the one I always forget because it's the only one that's a Greek letter on here. So micro is this weird looking M with a tail. Milli is just a plain old M. Centi is a C. Deci is D. Deca, which by the way we never use deca. You very rarely do you see those as a unit. Is DA. Hecto is H. Kilo is K. And mega is a capital M. Okay. Hecta and deca we do not use very much. They're just not normally used. The ones you'll see the most are mega, kilo, milli, centi, and micro. You might see nano a couple of times, but I'm not making you memorize that because you'll probably be able to look that up. Okay. All right. Okay. So, dimensions and units. We need to know the difference between a dimension and a unit. All right. So, dimension is a physical quantity that refers to the type of quantity it is. So, a dimension can be length or mass or time. Those are dimensions. Okay. Your unit is going to be kilograms or centigrams or decigrams. But your dimension is the gram. It's mass. Okay. So if we look at these two as an example, both of these are distances, 25 kilometers, 1.25 centimeters. The dimension for both of those is the same in that they are both measures of length, but the unit is different. One's a kilometer, one's a centimeter. Okay, so you need to know the difference because I may, when I'm correcting a paper or something, I might say your dimension was wrong. You need to understand that You put length and it should have been time or something like that. But if I say your unit is wrong, that means, okay, my dimension's right, it's length, it's just the wrong length. I forgot to convert my units, okay? So in equations, you have to have all the same dimension, okay? So just writing that down and we'll look at an example of what we mean. Physics is, the math is not terribly hard because it's just going to be solving an equation. The hard part is going to be figure out which equation do I need to use for which problem, because you're going to have a ton of them to choose from. So you've got to learn how do I choose which equation is going to fit my problem. And actually, even that, once you get the hang of it, is not that hard. Okay, you're going to pick the equation that has all the variables that your problem has, right? So if you're looking at force and mass and acceleration in your problem, you're not going to pick a formula for velocity because that doesn't have force in it, and it doesn't have acceleration in it, and it doesn't have mass in it. So you got to learn to look at your problem and look at what's in it, and then you find your equation that goes with it. Then you make sure all of your units cancel out correctly. And then that's really all there is to it. So when we get to vectors, it gets a little more complicated with vectors. That's where we have to throw in our sine and cosine and tangent. And other than that, it's not that much different. Okay, so let's clear this and let's go to the next screen. All right, so there's some examples of dimensions. The ones we've talked about are real easy because they're just mass and grams, mass and length and time. Those are easy. Ones that get a little bit different from what you're used to is ones like velocity, where we're going to take a length and divide it by a time. And we come up with a new unit. We call it a derived unit because we derived it. We made it. We took one thing and we divided it by another, and there's our unit. Okay. Acceleration is another example of that. You have length, you divide it by time squared. Okay, so again, this is in your textbook. It's a table in your textbook, so you don't necessarily have to write it down, and we'll be writing it down a lot in the coming days. So, all right, this is something I do want you to write down because this is what we mean by having our problems be dimensionally consistent. Okay, so here's what I want you to write down. Let's say we have this as our equation. Okay, lots of algebra in here, so lots of letters, and then we replace them with numbers. So x final equals xi plus vt. That just means your final distance, where you end up, is equal to where you started plus how fast you were going and how long you were going. That fast. Okay, that's all that means. I'm not worried about that part right now. What I do want you to notice is that when we put the units in here, final distance is length, initial distance is length, velocity is length divided by time, and time, of course, is time. So when we do all of that math, time cancels out, and all we're left with is length. That's how we know this is correct. I used the right formula, I got the right answer because my units, my dimensions are consistent. Time canceled out, left me with length all the way across. Okay? If this hadn't canceled out, you'd be like, oh, okay, something's wrong. I'm not using the right, something ain't right here. Which is why in this class, you cannot just put in numbers. You have to put in the number and the unit that goes with it. Because you have to make sure your units are going to cancel out and it's going to be dimensionally consistent. That's just a way to check yourself and make sure that you got your answer right before you have me say, no, that's wrong. Okay? It's just a way to double check yourself. So always make sure that your units will cancel out correctly and you have the same unit on both sides of your equal sign. Okay? Does that make sense? Okay. Does everybody have that written down? And perfect timing. We're left off. We'll do dimensional analysis tomorrow. Yay! Something to look forward to. Your safety test is your only homework for tonight. Okay, so just have that safety test done tonight, and then Friday or Monday we'll start doing problems. All right? Good, bad, ugly so far? How was it? Very good? Huh? Right now it's simple stuff. So just keep remembering we're starting with the simple stuff, and we're just going to add little bits. Just a little bit more every time. It's like when you weight train. You just add a little more weight every time. That's what we're doing. All right, y'all have a good day. See you tomorrow. Where you going there, Phil? Yes, ma'am.
Can I just hand these to you?
Oh, yes. Thank you. Yes,
I can
yes,
wait.
yes.
It's
No,
easier.
no. This is perfect. I
And
actually forgot to ask more.
the adult form, I wasn't sure what to do. I think it's this one. It didn't have a react signature, so I just signed it. It said adult, and I was like, oh shoot, but I've already done it because it said I am the person. Anyway, so
Yeah,
if
I
I need
know.
to redo that, I
Actually,
can.
yeah,
But-
if you could just cross your name out and have your parents,
Okay.
one of your parents sign it.
Yes.
Yeah, that's fine.
There is a schedule request form. It just says to turn it into a classroom teacher. You can't take it to the office.
Oh, okay. All right.
I don't know what you're supposed to do.
Okay. Thank you.
Oh,
Okay.
I'm not.
And you, all right. Thank you very much. Or Gamecock. All right. You gotta go all the way down that hallway, make the curve, and you'll just keep going straight, and you'll run straight into it. I believe her door, when you're in the hallway, there'll be two doors. Her door is this one on the left side. Keep walking till you run into the door.